dx, dy, dz, you change it to this little term, partial with respect to x, partial with respect to y, partial with respect to z. That just tells you that you're taking a partial derivative and that you have to hold the other variables constant when you take that derivative. So the take-home message here is that if this statement is true, then this term, the internal pressure, is 0 for an ideal gas. And because that term is 0 for an ideal gas, the total internal energy of an ideal gas is only a function of the temperature, because we only have those 3 degrees of freedom. We don't have the ability to store energy as potential energy. For real gases, that term is not 0, because you can imagine as a real gas expands, energy ends up getting stored as potential energy when you try to separate those gases from their attractive forces. And so if you were trying to hold temperature constant in a system that was expanding, well, as it expands, the gas molecules would be transferring some of their kinetic energy into a potential energy, and so they'd be slowing down, and they'd be that would cause a temperature drop in the system. And so if we wanted to hold the temperature constant, we would have to pump energy into the system to make up for the energy that was being stored as potential. And so that would be a non-zero value, positive. And it turns out that this becomes important in industrial processes, in particular the liquefaction of gases. So liquefaction of gases is mentioned at the end of chapter 1. I don't know why they mentioned it in chapter 1. It seems like that's a little bit early to be introducing it. But the liquefaction of gases takes advantage of a phenomenon that was discovered by Joule and Thomson in their Joule-Thomson experiment. And what Joule and Thomson did in that experiment was they took a gas in an insulated environment, so that no heat could enter or leave the system, and they pushed that gas through a pore, and they engineered this device in a way that held the pressure on this side of the container at a higher pressure than the pressure over here. And so they had a differential change in the rate of the piston movements. This piston moved at a rate that ensured that pressure was kept constant on this side at some P2 that was lower than P1. And this piston here pushed the gas over at a rate that ensured that P1 was constant. And what happened is, as they moved that gas from a low pressure to a high pressure, naturally it expanded, right? And as it expanded, again, some of its kinetic energy was bled off into a potential energy, and so the gas cooled. And what they found was that the temperature, T2, after that gas had been pushed through, ended up being lower than T1. So this was kind of the experiment where they showed that real gases do have attractive forces, and that as a result of that, in an isenthalpic expansion, in an adiabatic expansion like this, where you're not allowed to suck in heat from the environment, that an expansion would result in cooling for gases that had dominant attractive forces. It turns out that not all gases have dominant attractive forces. Some of them have repulsive forces that dominate under certain conditions. And for those gases, an expansion like this would actually lead to a heating of the gas. And so this you can use expansion of gases to cool them, and that's essentially what's done in the liquefaction of gases. If you have a gas at a hot temperature and you want to bring it down and drive into the liquid state, you can cool by expanding it. But other gases like hydrogen, you can actually heat by expansion.
Good question. What does that tell us? Since it's equal to 0,
It just tells you that that this term for an ideal gas is 0, and that so for an ideal gas, since that partial of the internal energy with respect to volume, so you're looking at how the internal energy changes as you're changing volume at constant temperature. For an ideal gas, that's 0. There's no energy that gets there's no kinetic energy that gets converted into other forms. And so to keep temperature constant, you don't have to keep injecting energy into the system to get an ideal gas to expand or contract. But real gases, when they expand or contract, end up bleeding off energy into other degrees of freedom. And so to keep temperature constant, you have to keep pumping energy into the system. Okay, so enthalpy. No, or very few processes in the real world happen under constant volume conditions. Constant volume conditions, we can look at the heat that's associated with the constant volume process, and that tells us what the change in the internal energy of the system was. And that's nice. It's nice to know, to be able to look at the heat that is bled off or fed into a process and understand what that means with respect to the internal energy of the system. But since very few processes occur at constant volume conditions, it's not, the internal energy becomes kind of an impractical way for us to think about energetic changes in systems in the real world. That's essentially what led to the birth of this concept of enthalpy. We know that when you look up the heats of reaction in the back of an intro Gen Chem text, you don't see delta U's. You're not looking at energetic changes, or you're not looking at the changes in the internal energy of the system. When you're looking at those heats of reaction, you're looking at delta H's, right? And that's because the change in this state function enthalpy ends up being, when we derive this, it ends up being the heat associated with a constant pressure process, a process that happens in the real world. And right now we're at 1 atmospheric pressure. If you have a reaction in a flask and it takes place under these conditions, then it's happening under a constant pressure of 1 atmosphere. So we want to develop essentially a state function that allows us to look at the heat transfer in a real world process and relate that heat transfer to some mathematical equation, right? So some math genius realized that for a constant pressure process, the heat transfer was a function of two things. They realized that it was a function of the change in the storage of energy in the form of these degrees of freedom, and it was a function of any work that was done in expansion or contraction of that system in the process. And so somebody decided that they would try to take the internal energy function and simply slap onto it this term PV, pressure times volume, and see what it got them mathematically. Remember that work, the expansion work in a system, ends up being for a constant pressure process and ends up being PEV. Similarly, pressure can change while volume is constant, and there'll be energetic changes associated with that. So this term, the PV term, essentially just augments the internal energy to account for that work that's done in expansion or contraction of a system. We need to start thinking about state functions again. State functions have exact differentials, so we can express the change in the function as the sum of the derivative with respect to one variable while holding the other variables constant times whatever change in that variable is, and we add to that the derivative with respect to the variable that we hadn't accounted for while holding the other ones constant. So state functions are these really cool things because they have exact differentials and we can perform mathematical manipulations on them, and also changes in state functions are path independent. They're only a function of the state. And this PV term ends up having an exact differential. So when we add PV to U, we generate another state function. So it turns out that, like the internal energy, the enthalpy is a function of state. And so changes in enthalpy can be calculated just by subtracting the enthalpy of one state from the enthalpy of another state, the enthalpy of the initial state from the enthalpy of the final state. It doesn't matter what path we take when we move from one state to the other. The difference in that enthalpy function, delta H, is the same regardless. So let's take and write out the differential of dH. We say that dH is equal to du plus dPV. First law tells us that du is dq plus dw, but dw is negative p external dv. We take the differential of pv, since it's a state function, we can write that out as pdv plus vdp. And because enthalpy is a state function, it doesn't matter what path we take as we evaluate these integrals. And so this work, or this term that represents work, p external dv, if we evaluate this differential on a reversible process where the external pressure is equal to the internal pressure, it becomes equal to this term, pdv. So those two terms cancel out, they go away. If we're looking at a constant pressure process where pressure doesn't change, that term, vdp, goes away, and we have the mathematical statement that the differential change in the enthalpy is equal to the differential change in the heat, Q, that is associated with that constant pressure process. And that gets us to this relationship, delta H is equal to Q, the heat associated with that constant pressure process. So now we can look at real-world changes that happen under constant pressure conditions, and we have a state function that we can associate with the heat that we see being consumed or evolved in a real-world process. Constant pressure heat capacity is differential change in Q or Q at constant pressure with respect to temperature, and that ends up being equal to the partial derivative of the enthalpy with respect to temperature at constant pressure, since all of this heat that's associated with a constant pressure process goes into changing that state function enthalpy. You can also write that the dq of a constant pressure process is equal to the integral of Cp dt. For real gases, if we want to evaluate a real gas, we can write out the total differential of dH just like we did for du. Total differential of the enthalpy is partial of the enthalpy with respect to temperature while holding pressure constant. Multiply that by the differential change in temperature, plus the partial of the enthalpy with respect to pressure while holding temperature constant, times that differential change in pressure. We just looked at the previous slide and we saw that the partial derivative of the enthalpy with respect to temperature for a constant pressure process is equal to Cp. So we can plug that Cp term in here. And so the total, we have the result of the total change in the enthalpy is equal to that Cp dt term plus whatever the relationship is between a change in enthalpy and the change in pressure. This term here becomes analogous to that internal pressure term that we looked at for the internal energy, and it essentially accounts again for any kind of attractive forces and energetic changes that happen when a system that does in fact have attractive forces undergoes expansions or contractions. For an ideal gas, there's no intermolecular forces, so the change in the enthalpy with respect to pressure ends up being 0, and we have the result that for an ideal gas, the total dH is equal to simply Cp dt. So if we want to change If we want to figure out what the change in enthalpy is, as long as we know that constant pressure heat capacity, we can integrate it with respect to temperature. Okay? For an ideal gas, there's a predictable relationship between the constant pressure heat capacity and the constant volume heat capacity. Because PV for an ideal gas is equal to NR, and we know that H is U plus PV, we can write out the change in H is the change in U plus the change in PV. We know that for an ideal gas, because the internal energy is only a function of temperature, that delta U is CV dt. We just said that for an ideal gas, delta H is Cp dt. PV is equal to nRT, N and R are constant, so any change in PV is a function of any differential change in T. So we can write out this expression, Cp dt is equal to Cv dt plus nR dt. Canceling out the dt's, we end up with that expression that Cp is equal to Cv plus nR. And I think I tried to derive that on Thursday, and I kind of got confused and messed it up. So ignore everything that I said about the relationship between CV and CP on Thursday, and pay attention to this. CP is equal to CV plus NR. And again, that's just saying that the heat that we have to put into a system at constant pressure is equal to the heat that we have to stick it into at a constant volume, plus some amount that accounts for that pressure volume work that the system does. Okay, so let's do a problem real quick here. So we've got a process. It's the combustion of ethanol. Okay. C2H5OH in the liquid state, combining with 3 oxygens in the gas state, forming carbon dioxide and water. 2 molecules of CO2 in the gas state, plus 3 molecules of H2O in the liquid state. You stick this thing in a bomb calorimeter, and a bomb calorimeter is a constant volume calorimeter, so no pressure volume work is done in that situation. And we measure that for 3.365 grams of ethanol. 99.472 kilojoules of energy is released. So you're going to need to know that for ethanol, our molar mass is 46.07 grams per mole. And that's it. What I want you to do is I want you to calculate for me delta U, and I want you to calculate delta H. And when you do this, remember, we're assuming that these gases behave ideally. And so your PV term would be whatever pressure volume changes that are indicated by ideal behavior. Go ahead and sit down and crank that one on, or crank that out for a second.